G'day, it's Richard Maher from Mars Classes. Again, today we're going to have a look at some very simple mathematics you can utilise to derive some equations in physics. We're going to use just purely algebra and some rearrangement and substitutions of equations to derive a couple of equations which you may not have seen derived previously. We're going to have a look at what are called SUVAT equations, and they're called SUVAT because we use the symbols S, U, V, A and T to represent the quantities which are being described. Now S stands for displacement because it comes from the Latin word which means spatial position. U stands for initial velocity only because U comes before V in the alphabet, and the initial velocity will come before the final velocity, which we represent with a V. A is represented by an A, understandably, as is time represented with a T. Now, again, understandably, a couple of equations you'll first encounter are the average velocity is equivalent to displacement on time. And that does make sense because when we look at the equation, the S on T, displacement on time, is metres on seconds, is metres per second. That's the units for average velocity. And when we look at acceleration, is the change in velocity on time. That's how we define acceleration, and because the units for velocity are metres per second, that's the units for acceleration. So those two equations are quite understandable. But then you're presented with a couple of equations which usually students are just told, just accept, just use, and we'll get by with them. What I'm going to do today is have a look at how we can derive those equations. So let's have a look at the situation where an object is going to move along a distance in a certain period of time. Now, what we've got here is this object moves 30 centimetres in 3 seconds. 30 centimetres is equivalent to 0.3 of a metre, and I don't know if you noticed, he started off faster and then maintained a reasonably constant velocity and then slowed down and came to a stop. So it's not the same speed all the way along, but if he did maintain that rate of change of position, we could describe his motion as having an average speed of 30 centimetres every 3 seconds, and then that could be expressed as 10 centimetres every second, or 0.1 of a metre every second. So when we're going to calculate this, if we use an equation to do it, we'd say the average speed is distance travelled on time of travel, and we'd look at the quantities of each of those things. And when we substitute them in, we'd come out with 0.1 metre per second. So that's all well and good in everyday parlance, but if you're in physics, you want a bit more information than that, because 0.1 metres per second could be travelling up or down or left or right or north or south. Who knows where it's going? So in physics, we like to have a look at directions of numerous quantities. And in fact, with motion, that's quite important to know what direction things are going. So let's have a look at this object now. And we can see he's done 30 centimetres to the east, or 0.3 metres east. And again, the time was 3 seconds, and therefore we can work out a quantity which is called the average velocity. Now, velocity is speed with a direction or change of displacement. So average velocity is displacement on time. Displacement is 0.3 metres east, and the time is 3 seconds. So it comes out to 0.1 metre per second east. So that equation, average velocity is displacement on time, we can rearrange and have it expressed as displacement is equivalent to average velocity times time. And if we're maintaining a constant acceleration, we can look at the fact that because it's accelerating against changing velocity, and if it's a constant change in velocity, the average velocity is also equivalent to the initial velocity, or the sum of the initial velocity and the final velocity divided by 2. Now, if we substitute in this expression here, u plus v on 2 for average velocity in this equation up the top, we can have that now rewritten as, hang on, I'll just get this all sorted out, rewritten as s equals u plus v times t. Now, that expression there, if we start to look at that and we realise that acceleration is the rate of change of velocity, and if we write that expression as a equals v minus u on t, and we rearrange that to express it in terms of what the final velocity is. Now, the final velocity is u plus at, and if we look at those two expressions we've now got, and if we substitute in for v, if we put in u plus at for v in this expression here, we can now get that whole expression written as what we've got here, which is equivalent to s equals 2u plus at on 2 all times t, and if we simplify that down, we get this expression here. And again, if we simplify it even further by dividing through by 2 on the numerator, we'll get that s equals ut plus half at squared. Now that's really neat. We didn't have to use any calculus or any graphing or anything like that, and we've derived that expression s equals ut plus half at squared. So let's bank that one away. Now let's have a look at what we've got here, and we can rearrange this equation now to have it expressed as what what time is, and we can have it as v take u on a is equivalent to time. Now instead of time, in this equation here, we can put in v take u on a, and we get this expression here. So on the denominator, we're going to have 2a. We can bring that up onto this side and have 2as. And if you look at that from your algebra, you know that these things here will give you the difference of squares, but let's just multiply it out to prove that. And the u's will cancel out, and we'll be left with an expression v squared equals u squared plus 2as. Again, really neat. What we've got is we've now got all 4 of the equations you normally use in rectilinear motion have all been done. And again, remember, if acceleration is constant, we've now got a way of explaining every one of those equations that you've used previously. Now, throughout upcoming videos, I'll look at how we can derive many other equations, things like Kepler's equations for planetary motion, or the movement of charged particles in magnetic fields, or even time dilation can all be derived really simply using just basic algebra or geometry or trigonometry. So until next time, I'll see you later.